Hi there, I'm going to show you how to calibrate a homemade test jig. We're calibrating for parasitic capacitance and parasitic impedances that cause this frequency response or the gain phase to be incorrect. Here's a zoom in on the test jig that we made with a bit of Vero board, 3 BNC connectors and a little mini grabber which we modified so that we can grab SMT components ranging in size from 0402 up to 1206 and maybe even bigger. Our goal is to calibrate this test jig so that we get good response from 1 kHz all the way up to 65 MHz. Let's start. Before we do our fixture calibration, let's just see what sort of response we get if we use a 50 ohm ZUUT. Here we go. I'm going from 1 kHz to 65 MHz using 2 volts signal generator amplitude. As you can see, we're measuring 50 ohms, but up at above about 20 MHz we see a change, and this is due to the parasitic components of the fixture impedance. Now what we can do is to calibrate this out. So we choose calibrate fixture. We're using a 49.9 ohm resistor. Research shows that the capacitance of the resistor is about 400 femtofarads with about a 1 nanohenry series inductance. We use this known resistor to calibrate our main reference resistor plus all the parasitics. Here we go. So we're generating the calibration table at the moment, which again is saved in the preferences file and also to any file that you might save with this captured waveform. Now we change to measuring the impedance, and this dims the calibration resistor. We're still using a 50 ohm reference, which is in fact what the BNCs are terminated in, and we start a suite. So now we see the 50 ohm impedance is seen right across the frequency spectrum from 1 kHz to 65 MHz, and the phase response is flat at around 0. We have calibrated this jig, and now when we go and measure other components, those components will be measured with a normalized transfer function and they will be correct. That's what we'll do next. But before we do, there's one final calibration that we can perform to improve performance and accuracy when looking at very low value capacitors, and that is to measure the open circuit capacitance of our test jig. We do that by removing any devices from the under test position of the test jig and starting a sweep. Now notice the signal to noise ratio over here. At the moment it's below 1, which means that we cannot make meaningful measurements. We need at least 3 to 1 before we can make measurements, and that's why the capacitance values don't appear until we get up in frequency. Looking at the capacitance value, we can see that this test jig has a capacitance of about 1 picofarad when it is open circuit. We're going to put that 1 picofarad into the C open compensation over here. Now we are compensating for the open circuit capacitance, and any capacitors of low value we measure will be more accurately measured. Okay, let's measure a couple of capacitors. I've taken a random 603 capacitor from my kit of parts and put it in the jig, and now I'm starting it and we'll see what it is. It's obviously larger than 10 picofarads. Now you can click the fit button to see it. It's a capacitor of around 90 nanofarads. Could be a Y5I one. As you can see, this capacitor is good for up to about 8 megahertz or so, 7 megahertz, and then it's falling off in capacitance up to 65 megs, where it's reduced its value down to about a quarter of what it started off with. Gives you an idea of how that capacitor could be used in a real circuit. Let's try another one. Okay, here's another one. I've placed it in the jig. I'll start the sweep and see what that one is. Obviously a lot smaller than the 90 nanofarads. We can click the fit button again, and we see it's about 220 picofarads, and as you can see it's good all the way up to 65 megahertz. Let's do one final one. Okay, here's the last one. It's already in the jig. I'll start sweeping. I don't actually know what it is. By my guess, at the low signal to noise ratio, it's probably pretty small. And it is. Right, we'll click fit. The low signal to noise ratio at low frequencies with a small value capacitor means that we don't get very accurate measurements of the phase angle, and so we get this variation in range. Once we get to 100k, it's not too bad. So here you can see its value is about 12 picofarads. 12 picofarads, yes. So very useful to see the performance of the capacitor, what it is. You can also check out its ESR, especially for higher value capacitors. This is useful when you're looking at carrying some ripple current. But you can see that by calibrating the probes and the fixture, we get very good accuracy up to 65 megahertz. Thanks for watching.